Can everybody hear me at home? And can everybody see the screen with the piece of paper on it?
Yes.
Yes, thank you very much. Kat, how you feeling?
Bruh,
Uh,
God hates me.
are you
Like,
minus an appendix?
I am. They told me I
Oh.
was septic when I came in. But I still waited 2 hours in the ER.
Man. This thing's been disconnected again, son of a biscuit. Well, I would say you look marvelous, but I can't see you. Oh, you piece of poo. Okay, I understand that. It's not working. It's like a Monday or something. Let's try it again. That looks like it might be live. Now I gotta do the old record. There. And I got a screen share with these other fellers. There. I'm almost learning how to do this. We got 2 weeks of in-person classes here. 1.5 weeks. We have today, we have Thursday, and then we have the test on the 23rd. Then you're off for Thanksgiving and you don't come back. Does everybody know you don't come back after Thanksgiving? But we still have our regular scheduled class at our regular times. We have class that's going to meet on the 30th of November and on the 2nd of December. The 2nd of December will be a Wednesday. That'll be our last day. Okay, so the 30th, I'll try to get most of chapter 9 covered. And we'll start chapter 9 next time as well. Today I'm going to do section 8.8. And then we'll talk a little bit about your test. Do you have anything that you'd like to ask me about web work? What's going on? We've got one. Okay, let's start with web work. From M1452, 3 minus 5 and 4. And we want to test if it's absolutely convergent, conditionally convergent, or divergent. It also wants to know all the different tests you can use. And our choices are chemical test, comparison test, conversion test, ratio test, okay. Well, for one, this is not an alternating series because the sign does contribute positive and minuses, but not in an alternating way. So we can't use the alternating series test. The ratio test works best under what circumstances? Ratio test, when would you use that? Radicals? You mean factorials? Factorials. Factorials and powers of n. So this doesn't have factorials or powers of n, so I'm going to eliminate trying to use the ratio test. Things that have n to a power work best with any kind of comparison test. So both the limit comparison test and the direct comparison test should work here. I'm not so crazy about integrating sine functions over powers of n. We would integrate powers of n times sine of n by parts, but not when the n's in the denominator. So I'm going to eliminate the integral test as well. I think this one works best with either kind of comparison test. But we're going to test for absolute convergence first. I'll do a mask swap here. This one's hard to talk through. Okay, this is much better. So I'm going to try any comparison tests. To test for absolute convergence, we put this in absolute value. So that's what I'm going to use. I'm going to test the absolute value of this series. We could also break it up into two series. We could look at 3 over n to the 4th minus sine over n to the 4th. And then see if we have the sum of two convergent or the sum of one convergent, divergent, that kind of thing. But I'm going to put it together because what you know about sines and cosines is that at their very largest, a sine is a 1. At its very smallest, the sine is -1. So what makes this numerator its largest is if I bound this sign by -1. So my largest numerator would be 4. The numerator is at its smallest when the sign is a +1. So I'm going to compare the sign to a +1 so that I compare this series to 2 divided by n to the 4th. Okay, so I'm going to say that since the sign of n to the 4th is smaller than 1, we're going to pick our comparison series to be 3 minus 1, or 2 over n to the 4th. What do you know about that series 2 over n to the 4th? It does go to 0, but that didn't help. It's a convergent p-series. This is a convergent p-series. Now I just made my numerator smaller by replacing the sign with a +1. If my numerator is smaller and my denominator is the same, then the overall size of this fraction is smaller than a convergent series. So I have that this part is smaller than this. And since in the direct comparison test, smaller than convergent is convergent, direct comparison test, smaller than convergent is convergent. Tells me that the series that I have right here is absolutely convergent. Now the limit comparison test should work the same way. If I divide this by that, then I'd have an n to the 4th on top and it would cancel. And the sign is bounded by 1 so that this limit is some version of a finite number. Do you like that answer? Nope. Series converges, comparison test, comparison test. Okay, take E. Let's not use the limit comparison test. Just the comparison test. Just the comparison test and not the limit comparison test is what this will take. Got another one? Anybody? Anybody at home have any web work you want me to work?
Yes.
Which one?
How about number, like the first part of number 1?
And what does the first part of number 1 say?
It's the same kind of question you just did. It's the sum from n equals 2 to infinity of -1 to the n minus 1, and then root n over 1 plus 2 root n.
Okay, so we have to pick what we want to use on this thing. So this part tells me that it's very possible to use an alternating series test.
Oh wait, you're gonna be mad. That was the wrong question.
We're going to do it anyway because it's a quickie.
Okay, that's 4A, by the way.
I'm sorry,
4A.
this was 4A?
No, the one I just gave you.
The one you just gave me is 4A. Okay. All right. So what do you see when you look at the non-alternating part? Anything jump out at you on that non-alternating part? I'm sorry? It's going to diverge because? Yeah, the limit's not 0. The only series that have a chance of converging are those whose non-alternating term goes to 0. And this one has a non-alternating term that goes to a half. So this series diverges by the test for divergence. It's not absolutely convergent by the test for divergence. And it's not conditionally convergent by the alternating series test, because the limit as n goes to infinity is a half. Either one of those tests require the limit to be 0. So always kind of eyeball it. Make sure the general term goes to 0. All right, Kat, which one you want me to really work?
Number 1, part 1, which is the sum from 1 to infinity of 1 over n squared minus 3. And it's the one where you like say what tests you use and the
so
first.
n squared minus 3, and there's nothing on top, just a 1?
Right.
Good. Okay. Okay. Now, n squared minus 3 on the bottom is going to go to 0, so we got to do try some other tests. And let's see, our choices. We're going to suspect that it converges, right? Because of the n squared. So we're already thinking in terms of comparison tests. Either comparison test will work. And if you work to, it's messy, but you could integrate this. You could probably do a partial fraction decomposition to integrate this. So the integral test will be way down my list of tests, but I think we're going to show that this converges either by the direct comparison test or by the limit comparison test. Well, let's try the direct comparison test. We suspect it's going to converge. Does it look like my series is smaller than a convergent series? Well, I compare to the series 1 over n squared, which is a convergent p-series. But what I did to make this is I made my denominator, this denominator, n squared, is bigger than n squared minus 3. So when I flip these over, 1 over n squared minus 3 is bigger than 1 over n squared, which is the wrong direction for the direct comparison test. This is a convergent series, and my series is not smaller than it. So we can't use the direct comparison test, which means our choice will be the limit comparison test. In the limit comparison test, you take the given series and you divide it by the comparison series, and any positive finite limit says both series do the same thing. And with a little flip and multiplying step, we'll get an n squared on top and an n squared minus 3 on the bottom. So I do get a positive finite limit. Positive finite limit. So both do the same, which means our series is absolutely convergent by the limit comparison test. So I don't know if you would want to enter integral test on this, because I don't think I'd want to try the integral test on this since it's so easy to do a comparison test with.
It did take the integral test. It took convergent, integral test, the limit comparison, and the direct comparison.
It took the direct comparison. It goes the wrong way for the direct comparison.
I don't know.
Okay. Maybe it says
Can you also do number 13?
lucky number 13. All right, what you got here on number 13?
So the limit from, or I mean the sum from k equals 1 to infinity, k squared times x minus 2 to the k over 3 to the k.
And we're going to find the interval of convergence.
Yes.
So when you find the interval of convergence, our choices are to either use the ratio test or the root test. Tell me why I'm not going to use the root test. Yeah, this one term here messes me up. It doesn't have a k power. So even though the other ones do have a k power, don't do the root test when you've got a non-k power, because that involves a more complicated limit. So let's just do the ratio test. We set up the limit as k goes to infinity of the k plus first term divided by the kth term. We want it to converge, so we want to find the values of x that make that smaller than 1. So the k plus first term would look like k plus 1 all squared, x minus 2 to the k plus 1 divided by 3 to the k plus 1. Absolute value. Now we're going to divide by that. So let's flip it up and put the 3 to the k here. K squared, x minus 2 to the k. We want that smaller than 1. So I'm just going to write this as x minus 2 to the k times x minus 2 to the first. And I'm going to write this as 3 to the k times 3 to the first. I'll just put that extra step in today. I should have limit written in front of this. I've lost that quite a bit ago. My limit right here. Now we can cancel. Cancel the x minus 2 to the k. Cancel the 3 to the k. And pull out this x minus 2 in absolute value bars. Everything else deals with k's. On top, I'm just going to have a k plus 1 squared. And on the bottom, I'm going to have a 3k squared. Anybody want to take a stab at what that limit is right here? 1/3. This is going to be a k squared if you were to multiply it out with a coefficient of 1. Here's a k squared with a coefficient of 3. And when they have the same powers, you just pluck off the coefficients. So that limit's 1/3. That gives us that x minus 2 times 1/3 smaller than 1 implies that x minus 2 is smaller than 3. That 3 over there is called the radius of convergence. But saying that x minus 2 is smaller than 3 is the same thing as saying that x minus 2 lies between 3 and negative 3. And now get the x by itself in the middle by adding 2 to each side. The negative 3 plus 2 puts a negative 1 here. 3 plus 2 puts a 5 there. Now we need to go back to the original expression and check the endpoints, put in those x's, and see what kind of series we get, a convergent one or not. Let's start with x is equal to negative 3. If x is negative 3, I have the series that has a k squared.
Are we not going to use x equals -1?
I'm putting x is negative 1, and when I put in negative 1, it adds to a negative 3. My mouth went without my head. Negative 1 minus 2 gives me a negative 3. How do negative 3 to the k and 3 to the k cancel? What's left? Negative 1 to the k. That's right. Do you think the alternating series minus 1 to the k times k squared is going to converge or diverge? Because the limit's not 0, right? This diverges because the limit k goes to infinity of k squared ain't 0. So we leave that as an open endpoint. The same thing's going to happen when x is 5. Because if x is 5, I'm going to get a positive 3 right here. And again, I have a general term that does not go to 0. So it diverges at both endpoints. The interval of convergence is an open interval from -1 to +5. It converges absolutely for all numbers between -1 and 5, and it diverges elsewhere. You like that one?
Yes, thank you.
Anything else?
Nope.
Anybody else? It's kind of fun stuff, isn't it? It is. You can admit it. We're all nerds in here. But none of your regular friends are seeing you. Okay, so I started talking about how to make a Taylor series last time. And remember, it's a power series that has an x minus c, power series centered at c, so that on its interval of convergence, the power series matches the graph of some particular function that we're building it from. So let's see, that's page 1. Here we go with page 2. And so Taylor series, section 8.8. Taylor series for f of x is equal to something. F of x centered at x is equal to c. I'm about to write down the formula, but what we need out of this particular function is that it has an infinite number of derivatives defined in an interval containing c. F has to be such a function that all of its derivatives are defined in an interval containing c. Because to build this Taylor series, we say that f of x matches this polynomial. It has the same y-intercept, then it has the same slope. Make it centered at x minus c. This will be to the first power, and this is over 1 factorial. Then the second term has an f double prime at c times an x minus c squared, and it's over 2 factorial. And so we continue on this way so that the order of the derivative matches the power on the x minus c, which matches the factorial. So let me put this here, put plus. We're going to have the nth order derivative at c times x minus c to the power of n all over n factorial. And we do this from n is 0 to infinity. So this is a polynomial, an infinite degree polynomial that fits the graph of y is equal to f of x on its interval of convergence. If we choose the number c to be 0, then we have something called the Maclaurin series. So Mclaren series looks like f of x is equal to f of 0 plus f prime at 0 x over 1 factorial plus f double prime at 0 x squared over 2 factorial, and on and on and on, so that the order of the derivative at 0 is multiplied by x to the power of n divided by n factorial. So typically we like to use Maclaurin series unless we're dealing with something like a logarithm and we have to move it away from 0, or 1 over x to a power. We have to move those away from 0. Trig functions, sometimes for our applications to differential equations, we need those to be shifted a bit every now and then, depending on what it is that we're modeling with our trig functions. So they're really easy to make, but then we're going to have a list of Maclaurin series that would be helpful if you knew them, so that we can build other series quickly from them. So I'm going to show you how to make some Taylor series first, and then we're going to look at some of the basic Maclaurin series. All right, so let's start with this one. This is a worksheet that I had on Blackboard. If you guys wanted to pull it up sometime and try it yourself. Find the Taylor series for f of x is the square root of x centered at x is equal to 1. So we're going up here with the value c is 1. What we'll need to do is take a bunch of derivatives of the square root of x until we can kind of see a pattern, and then plug it into the formula. Sometimes we're able to come up with a general formula right out here, and sometimes not. Let's just take a look at it and be patient with it. So I'm going to think of that as x to the 1/2. I'm going to make a column for f and all of its derivatives. And I'll just take a handful of derivatives till I run out of room. F prime of x is 1/2 x to the negative 1/2. F double prime is negative 1/4 x to the negative 3/2. The third derivative is 3/8 x to the negative 5/2. The fourth derivative is a negative 15 over 16, x to the negative 7/2. And maybe I'll go one more. Negative 7 times negative 15 is a positive 105. 16 times 2 is 32, and that'll be x to the negative 9/2. Next, we need to evaluate each of these when x is 1. And that's, I don't have to simplify because 1 to any power is going to be 1. So in each of these cases, evaluated at 1 will just give me the coefficients. So f of 1 is 1. F prime of 1 is a half. F double prime of 1 is a negative 1/4. F triple prime at 1 is positive 3/8. Fourth derivative at 1 is a negative 15 over 16. And the fifth derivative at 1 is 105 over 32. And now I'm just going to recopy this formula here on this page so I don't have to keep looking back and forth. So I'm going to write a Tander series f of x that looks like f of 1 plus f prime at 1 over 1 factorial times x minus 1 plus f double prime at 1 over 2 factorial times x minus 1 squared plus the third derivative at 1 over 3 factorial x minus 1 cubed. I think I got room to put the other two terms. No, I don't. I'll just put dot, dot, dot. You see the pattern. It's a very, very easy formula to remember. Now let's fill in our numbers. So my f of x is the square root of x. F of 1 was 1. F prime of 1 is a half. 1 factorial is just 1. F double prime at 1 is a negative 1/4. Let's put it over 2 factorial. And then an x minus 1 squared. F triple prime at 1 is 3/8 over 3 factorial. X minus 1 cubed. Fourth derivative is a negative 15 over 16 times x minus 1 to the fourth over 4 factorial. And then plus 105 over 32 over 5 factorial, x minus 1 to the fifth. So I'm looking at if I want to simplify this. I'm thinking, are there any simplifications in here that would give me something nice? 2 factorial is just 2. 3 factorial is 6. 4 factorial is 24. And 5 factorial is 120. So does that help in any way? Well, let's see. Does it look like it's going to simplify to anything pretty? Not really. I think I'll just leave it there. I'll just leave it like that. Any questions? Easy enough? Okay, we go on to my second example. So let me make a note here. There are times in which we can write the general formula for this nth term. But in most cases, that's hard to do, like in this case. Some cases, it's easy to do. So before I do the next example on the worksheet, the case in which it's easy to write a general term is, for instance, the Maclaurin series for f of x is equal to e to the x. Let's do that real quick, because all derivatives of e to the x are e to the x. And it's a Maclaurin series, so we're choosing x to be 0. All the derivatives evaluated at 0 are going to give me 1. So let's bop over here to my other page. Right here. Write a Maclaurin series for f of x is e to the x, and it's going to be easy to write the general formula. So let's also determine the interval of convergence. So I'm going to start the same way. I'm going to make a column for f and all of its derivatives, and then the second column will be all those values at 0. Don't have to go very far. Let's just go 2 derivatives, because all of them are the same. And now evaluated at 0, since it's a Maclaurin series, e to the 0 is 1. So all derivatives and function evaluations at 0 are going to be 1. And so the formula for the Mclaren series is right above here, but I'm going to write it right here again. It'll help you remember it if you write it down each and every time. That's what the general term looks like for Mclaren series. So all of our little pieces here are going to be 1s. So you'll just have 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared all the way out. So we have that e to the x is equal to 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared. We'll have 1 over 3 factorial x cubed. And so that's going to look like 1 over n factorial x to the n. See how easy it was to get that formula? The point of having the formula is now we can determine the interval of convergence by doing that ratio test. Find where the limit of the an plus first term divided by the anth term is smaller than 1. The limit is an n, so n goes to infinity. An plus 1 divided by an smaller than 1. So the an plus first term would have an x to the n plus 1 divided by n plus 1 factorial. Times, I put this x to the n down here and this n factorial here. This time I won't write out how I'm going to cancel. I'll just cancel it in this step. This x to the n here will cancel that one, just leaving the x to the first. And n factorial cancels the n factorial behind the n plus 1. And so I just have an x to the first power and an n plus 1 on the bottom. I take the x to the first power out here. And then we have a 1 over n plus 1 in here. What is the limit of 1 over n plus 1 as n goes to infinity? 0. So what happens when this limit is 0? That's right. I have whatever x times 0 is smaller than 1 no matter what x is. So the interval of convergence is over the entire number line. Okay. Now, if I added a part B and said find the Maclaurin series for e to the x squared, don't start all over. Look how messy it would be if you found the Maclaurin series for e to the x squared by taking a bunch of derivatives of e to the x squared. You'd have to do the chain rule, which would put a 2x in front of this one. Then you'd have to do the product rule in the chain rule, and you'd get big, long derivatives. We can build other Maclaurin series from basic Maclaurin series because on its interval of convergence, we can do term-by-term operations. We can multiply by an expression. We can do function substitution. We can do term-by-term derivatives, term-by-term integrals. So I claim that if I want to find the power series for e to the x squared, I just go back up in here and I replace each x with x squared. So I would have a 1 plus x squared over 1 factorial plus x squared squared, which would give me x to the 4th over 2 factorial. X squared cubed is x to the 6th over 3 factorial. Go in here. I would have x squared to the n, or x to the 2n, over n factorial. And then if I wanted the power series, say, for the integral of e to the x squared, well, I don't have to start at the beginning. I can just integrate each term. So let me put that on the next page. Power series for the integral of e to the x squared dx is found by doing term-by-term integration. So the integral of e to the x squared dx is the integral of 1 plus x squared over 1 factorial, x to the 4th over 2 factorial, x to the 6th over 3 factorial, x to the 2n over n factorial, like that, dx. We integrate this one and get x. Integrate that and we get x cubed over 3 times that 1 factorial. Integrate this and get x to the 5th over 5 times 2 factorial, and so on. Integrate that, I get x to the 2n plus 1 over 2n plus 1 n factorial. And this should converge over the whole number line. We also have a constant of integration, so sometimes they just write the constant up front. So don't always start by taking a bunch of derivatives. If you have a known series, we can do term by term operations. So I want you to think on number 2 here, how we're going to find the Maclaurin series for f of x is 1 over 1 minus 2x. Notice that that is defined at x is 0. We need our Maclaurin series to define in some interval containing 0. It's not hard to take a bunch of derivatives of this and then evaluate it at 0. I'm going to do it that way, but then I'm going to show you the easier way. So we'll do it the long way first, and then we'll do it the quick way. Let's start with this. Think of it as 1 minus 2x to the negative 1 power, and take me about 5 derivatives of that. The derivative inside is always just a constant, so I never have to do the product rule or the quotient rule beyond any of my derivatives. It's an easy enough function to build from scratch. So the first way we're going to do this is using the general formula. Think of f of x is 1 minus 2x to the negative 1. So that f prime of x is minus 1 minus 2x to the negative 2, and the derivative inside is a negative 2. So I'm going to simplify that to a positive 2, 1 minus 2x to the negative 2. Now my second derivative, let's kind of simplify it as we go. Keep in mind that we're always going to get a negative 2 from the derivative inside. So when I take the derivative outside, I'm going to get a negative 4. Now multiply that by the negative 2. And so we get a positive 8, 1 minus 2x to the negative 3. Now think ahead. Tell me what the number in front of the 1 minus 2x to the negative 4 is going to be. A positive 48, right? You've got negative 3 times 8 is a negative 24, times the negative 2 inside gives you a positive 48 out front. I'm going to do one more just for the hell of it, the heck of it. I'm going to get a negative 4 times 48 times another negative 2, or a positive 8 times 48. 8 times 8 gives me 64. 4 times 8 is 32, plus 6 gives me 384 in front. Let's stop there. Now it's a Mclaren series, so we have to evaluate all of those guys at 0. When you put a 0 in here, inside the parentheses, you're going to end up with a 1. 1 to any power is 1. So f and f prime and all of the derivatives at 0 are just going to give me the numbers out front. F double prime, got one too many primes there. Now I'm going to use the margin there on the right to write down the formula for the Maclaurin series. That f of x will look like f of 0 plus f prime at 0 over 1 factorial times x to the first, f double prime at 0 times x squared, that's over 2 factorial. The third derivative at 0, x cubed over 3 factorial, and so on. So our f of x is 1 over 1 minus 2x. Our f of 0 is 1. Then we have plus 2x over 1 factorial plus 8x squared over 2 factorial plus 48x cubed over 3 factorial plus 384 x to the fourth over 4 factorial, and so on. We do need to see if we can simplify this because we're going to want to know what the interval of convergence is. So let's see if these simplify nicely. 2 factorial is just 2. So 2 will go into 8, leaving me a 4 here. 3 factorial is 6. 6 goes into 48 8 times. 4 factorial is 24. Let's see how many times 24 goes into 384. $16 times. So I can write this as 1 plus 2x plus 4x squared. You said that was 8x cubed, 16x to the fourth, and so on. So look at the numbers in front of the x to the power. This is 2 to the first, 2 squared, 2 cubed, 2 to the fourth. So I can rewrite this now as 1 plus, let me put it like this, 2x plus 2x squared plus 2x cubed plus 2x to the fourth. Do you recognize that kind of series? Subsequent terms are just a multiple of the previous term, and it's a fixed multiple. It's a geometric series where my multiplier is 2x. This is a geometric series with r is equal to 2x. And so our geometric series converge if r in absolute value is smaller than 1. So we put the 2x in there. I can take the absolute value of 2 and get 2. So I can divide all this by 2. And so our interval of convergence is that. I don't need to plug in the 1/2. I really can't because this function is not defined when x is a half. It is an open interval from negative 1/2 to positive 1/2. And that was the long way to do it. And that's the secret to how we do it in the short way. A geometric series has a known sum. What's the sum of a geometric series whose first term is a and whose multiplier is r? What's the formula for the sum? A over 1 minus r. This has that form of a over 1 minus r. Right? The sum of a geometric series. So this already has that form. So I could just spit out the geometric series. A is 1 and R is 2x. If A is 1 and R is 2x, I have this line right here. So had you recognized it from this step, that you have the sum of a geometric series, you can just go from this step right down to this step and skip all the derivatives. So let's mimic that. I want you to look at this example, and I want you to write me a power series for the ratio 1 over 1 plus x squared. So let's go over to, see if that's over here. Nope. So use the idea of number 2. To write the power series, which will be a Maclaurin series, since it's centered at 0, for 1 over 1 plus x squared. Interpret 1 over 1 plus x squared as being the sum of a geometric series where A is 1, and what would you use as R? That, right? That has the form of A over 1 minus R. A over 1 minus R comes from a power series that looks like A plus AR squared plus AR cubed. So in our example, A is 1, R is a minus x squared, where the minus comes after the squaring. So 1 over 1 minus a negative x squared should have a power series that looks like 1 plus 1 times negative x squared plus 1 times negative x squared squared plus 1 times negative x squared cubed, like that. Now let's simplify it. 1 over 1 plus x squared looks like 1 minus x squared plus x to the 4th minus x cubed. It's an alternating series. So let me put a minus 1 to the n plus 1. Start n at 0. All the powers on the x's are even numbers. So I have something like that, x to the 2 times n. If n is 0, well, if I better start n is, yeah, I should start n is 0, but that means I just want negative 1 to the n here. Right, so my first term is a positive 1. Then my second term is a negative 1. Third term is a second term. N is 0 gives me that. N is 1 gives me that. N is 2 gives me that. So I'm okay. So there's the power series for 1 over 1 plus x squared. But if you know the power series for 1 over 1 plus x squared, then you certainly can figure out the power series, say, for the arctangent of x. How is the expression 1 over 1 plus x squared and the arctangent of x related? The arctangent of x is the integral of this, right? So if I want now to work backwards and get the power series for the arctangent of x, I just integrate this term by term. So from this, we can find Mclaren series for the arctangent of x. But tangent of x is the integral 1 over 1 plus x squared dx. So we just integrate this. Just go to the summation form. This is a constant. I can factor it out. Integrate x to the 2n by adding 1 to the power and dividing by the new power. So there's the power series for the arctangent of x. Again, you would not want to generate the Maclaurin series for this by the general formula, finding f, f prime, f double prime, f triple prime. Because man, once you get past f prime, you're going to be doing the quotient rule from there on out. And that'd be too time consuming, where this was really easy. Okay, so number 3, find the Maclaurin series for f of x is the natural log of 1 plus x and state its interval of convergence. So we can start with the natural log of 1 plus x and take a bunch of derivatives. That's not going to be hard. Or we can think of the natural log of 1 plus x as what we get when we integrate something. What do we integrate to get the natural log of 1 plus x? 1 over 1 plus x. That would be easy to write as a sum of a geometric series. So instead of taking derivatives, we're going to note that the integral of 1 over 1 plus x is the natural log in absolute value of 1 plus x, plus some constant of integration. 1 over 1 plus x has the form of a over 1 minus r, where a is 1 and r is a negative x. That's the sum of a geometric series, so it should expand as a geometric series. A plus AR plus AR squared plus AR cubed, and so on. Right. So let's integrate that now. So the natural log of 1 plus x, well, before we do that, this thing converges for r in absolute value smaller than 1. R is negative x in absolute value, so that's the same thing as saying that x is smaller than 1. That's the interval of convergence. X is between negative 1 and 1. It's going to be an open interval because when x is negative 1, this isn't even defined. So when I now integrate term by term, it has to only be on this interval of convergence, which means I no longer need the absolute value bars. 1 plus x for numbers between -1 and 1 is always positive. So I'm just going to integrate that. It's the integral of all of those guys. That is -1 to the n, x to the n, with my summation here. And we'll get x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. Or in summation form, it looks like -1 to the n, x to the n plus 1 over n plus 1 plus some constant of integration. So the moral of the story is, if there's a shortcut, take the shortcut, unless you're not into shortcuts. So we should know the Maclaurin series or geometric series, a over 1 minus r. From that, we can get the Maclaurin series for just about anything. We should memorize the Maclaurin series for e to the x. Two other Maclaurin series that would be handy to know are those for the sine of x and for the cosine of x. So let's do that. Let's generate the Maclaurin series first for the sine of x. Take a bunch of derivatives of that. It's a Maclaurin series, so we have to evaluate a bunch of derivatives when x is 0. Derivative of sine is a cosine. Derivative of cosine is minus the sine. I'm going to do about 6 of these. Actually, that's all I need to do, because then they're going to reproduce themselves, right? I'm going to get into an infinite loop. The fourth derivative gives me a positive sign, so the next one will be cosine, minus cosine, sine. My derivatives are going to start repeating themselves. So I'll stop there. For Maclaurin series, we need to evaluate those at 0. What's the sine of 0? Sine of 0, 0. Cosine of 0 is 1. So we're going to get zeros everywhere we have a sign, and either a 1 or a minus 1. Now we're going to write our Maclaurin series. Formula again is f of x is equal to f of 0, f prime at 0 over 1 factorial times x, f double prime at 0 over 2 factorial times x squared, f triple prime at 0 over 3 factorial times x cubed, blah, blah, blah. So we have over here the sine of x, f of 0, f double prime at 0, the fourth derivative at 0. Every even derivative of 0 will be 0. We have 0 plus 1 over 1 factorial x plus 0. I'm not going to put the rest down. Over here, I have minus 1 over 3 factorial x cubed. The next one will be 0. And then the next power of x I'm going to have is going to be a positive 1 over 5 factorial x to the 5th. Agreed? The next term will be 0. Somebody tell me what the next term is. Negative 1 over 7 factorial x to the 7th. Now let's see if we can write that in a general formula. What we need to be able to write is that we're going to have only odd powers on x, and whatever is the power on x will be the same as the factorial underneath the coefficient, and they alternate in sign. So can you write that as a general formula? I need something to alternate, so I got to figure out a power up here. And then I need odd powers on x. And whatever that power is going to be down here with the factorial. So how am I going to make an odd power?
N minus 1.
Take any number and double it. And automatically it's even, right? Get the odd one, go right next door. So I can write that as 2n minus 1 or 2n plus 1. Doesn't matter. Let's see, if I did a plus 1, then I can figure out what I want my n to be here. Then I need a 2n plus 1 here. I want a 1 factorial as my first term, so I'm going to start my n at 0. I want my first term to be positive, so I can make this n right here, because negative 1 to the 0 will give me a positive 1. So there's the formula for the sine of x. It's an alternating series. X to the odd power divided by odd power factorial. Have you ever heard that the sine was classified as an odd function? Odd functions are symmetric to the origin. One period of sine here is the opposite across the y-axis. Cosines are even functions. And I can get the power series for the cosine function using the fact that the derivative of the sine is the cosine. So let's take the derivative of this general formula. So to get the power series or the Maclaurin series, for the cosine of x, just take the derivative with respect to x of the sine of x. So we're going to take the derivative of this general term here. And we get that the cosine of x will look like, well, let me just show you what it would look like if I took the derivative of the first few terms here. Ignore the zeros. The derivative of that x is just going to give me 1, and it'll be positive. Then the next one will have a 1 over 3 factorial. Then I'll have a 3x squared. Then the next one I'll have a positive 1 over 5 factorial, 5x to the 4th. And then the next one will be a negative 1 over 7 factorial, 7x to the 6th. But 3 factorial and the 3 have a common factor of 3. 3 factorial is 3 times 2 times 1. Same deal here. 5 factorial is 5 times 4 times 3 times 2 times 1. I can cancel this 3 with that 3, and it leaves me a 2 factorial. Cancel that 5 with that 5, and it leaves me a 4 factorial. Cancel that 7 with one of those 7s, and I'll have a 6 factorial. Then to see what the general formula looks like, let's just take the derivative up here. We'll have a minus 1 to the n, bring the power down, raise it to 1 power less, and then I've got the 2n plus 1 factorial. So with my summation here, I'll have my alternating term, 2n cancels the 2n plus 1 first term in the factorial and leaves me 2n factorial left. And then an x to the 2n here. But my first term is going to be a 1, so remember that when you take a derivative, that moves the counter up 1. But then that makes my first term negative, and I don't want that. But it does make, I do want my counter at 0, so let me go back to 0. So that gives me a negative, that's x to the 0, that 0 factorial, that's there. And then there's one that's minus squared 2 factorial, that'll work, leave me with it, and is 0. So the cosine expansion is an even function, just like you thought it would be. We could do the ratio test to find the interval of convergence. One's the derivative of the other, so they should have the same intervals of convergence. Let's use, I don't care, let's find the interval of convergence for this power series here. Find the interval of convergence for the cosine of x. Using this general term, we're going to take the limit as n goes to infinity of an plus 1 over an and set it smaller than 1. We don't have to worry about the minus 1 to the n because it's an absolute value. That'll always be a positive 1. So let's use this general term and look at the limit as n goes to infinity. This will now be an x to the 2, and now replace n with n plus 1. Down here, we have a 2 times n plus 1 factorial. Then we divide by that term, which gives me a 2n factorial here, and an x to the 2n here. Are you with me? The 2 times n plus 1 gives me x to the 2n plus 2. Then I'm going to have a 2n plus 2 factorial, then a 2n factorial, and an x to the 2n. You get a little bit of canceling. Take the x to the 2n's out, and it leaves me an x squared. Pull that out in front. How is my 2n factorial and my 2n plus 2 factorial going to cancel? So the 2n factorial cancels and leaves me 2n plus 2 times 2n plus 1. So all of these guys here will cancel. This is what's left. And it's going to be down here in the bottom. And so, what's that limit? Bunch of n's on the bottom, the 1 on top. That limit's 0. And when the limit is 0, what does it mean for the interval of convergence? It's all real numbers, right? This limit is 0, so it converges for x all over the number line. So this power series here for the sine of x you should learn the alternating series, just like that for the cosine. This power series you should learn, as you should learn the power series for a geometric series. Now. We're going to use, let me start numbering my pages a little bit better. Oh, I got 2 page 2s. This has to be page 3. This is page 4. Somewhere in my worksheet here inside there. Okay, so use the Maclaurin series to find power series for 3x squared cosine of 5x. So I'm going to remind you what the cosine of x was. There's the power series for the cosine of x. So if you know the power series for the cosine of x, it should be real easy to get the power series for the cosine of 5x. By doing what? Every x you see in there, replace it with 5x. So first, power series for the cosine of 5x. I'll put it in here, and then I'll put it in here so that you can see it. It looks like 1 minus 1 over 2 factorial times 5x squared. That's 1 over 4 factorial times 5x to the 4th minus 1 over 6 factorial times 5x to the 6th, and so on. In terms of the summation, we're just replacing x with 5x. Everything around it stays the same. Term by term substitution. Now, when you multiply a sum by something, you distribute it. So multiplication is a term by term operation. So the power series for 3x squared times the cosine of 5x, just multiply each of these terms by 3x squared. So we put my 3x squared here. put it in here. In summation from n is equal to 0 to infinity minus 1 to the n times 3x squared times 5x to the 2n over 2n factorial. But I'm going to simplify that a little bit. Here I'm going to have an x squared. Here I'm going to have an x to the 2n. And when you multiply like bases, you add exponents. So I can combine these x's as x to the 2n plus 2. This is 5 to the 2n times 3. I'm just going to pull it out as 5 to the 2n times 3, because that's a constant. Like that. And so if you believe that, my next one on the worksheet says find the Maclaurin series for the integral of 3x squared cosine of 5x dx. Remember, if you integrated this, we could do it by parts, and you'd have to integrate it by parts twice. This one we can integrate just by integrating term by term. So let's integrate it by integrating this general formula. So from our last page, the integral of 3x squared cosine of 5x dx is just the integral of the sum from n is 0 to infinity, negative 1 to the n, 3 times 5 to the 2n, x to the 2n plus 2 over 2n all factorial. The interval of convergence is still the entire number line. On the entire number line, I could swap places with the summation symbol and the integral form, the integral symbol. This is a constant. This big boy right here is a constant. We integrate by adding 1 to the power and dividing by the new power. And so we're going to get our constant. We're going to get our other constant. It's still a series. Add 1 to the power gives us x to the 2n plus 3 and divide by the new power. Just keep beating the same drum. My next example wants the power series for the derivative of 3x squared times the cosine of 5x. Keeping that in mind, the power series for the derivative of that, well, just think about taking the derivative of that. Good Lord, this product goes all over the place. We just have to take the derivative of this. So we'll pull that up. The Mclaren series for the derivative of 3x squared cosine of 5x is just the derivative of the power series for the 3x squared cosine of 5x. So from my last page, that was the sum from n is 0 to infinity of negative 1 to the n, 3 times 5 to the 2n, x to the 2n plus 2, all over 2n factorial. All of this muck is a constant. You can pull it out. Then you bring the power down, raise it to 1 power less. But again, the derivative starts to counter then at 1. So we'll have the summation from n is 1 to infinity. This will be here. This will be here. This will be here. And I bring the power down, raise this to 1 power less. Okay, find the first 4 terms of the Tander series for x natural log of x centered about a is equal to 2. So that a is the same as the c that I used in the formula. Did you see something? Let's see that. So we'll do this on paper. Find first 4 terms of the Tander series for f of x is equal to x ln x centered about a is equal to 2. So if you want 4 terms, it's easy enough just to take 4 derivatives. Well, actually, we don't need 4 derivatives. The first 4 terms would look like this. So my formula f of x would be f of a plus f prime at a over 1 factorial x minus a plus f double prime at a x minus a squared over 2 factorial. Then the 4th term would be the 3rd derivative. So you're doing that with our function, and a in our example is 2. So let me give you a few minutes to try it on your own. All right, I'm gonna catch up with you. Let's just do it by brute force by taking derivatives. This little horsey thing out of the way here. Okay, so I'm gonna need all the way down to the third derivative. Starting with f of x is x ln x, f prime of x, the first times the derivative second, plus the second times the derivative first. So I get 1 plus the natural log of x. The second derivative is just going to be 1 over x. And the third derivative is going to be a negative 1 over x squared. Agree? Now I'm going to evaluate all of those at 2. So f of 2 looks like 2 ln of 2. F prime at 2 looks like 1 plus the natural log of 2. F double prime at 2 looks like 1/2. And F triple prime at 2 is a negative 1/4. So now we put it all in there, and we have the first 4 terms for x natural log of x is f of a, 2 natural log of 2. F prime of a is 1 plus the natural log of 2 over 1 factorial times x minus 2. The second derivative is 1/2 over 2 factorial x minus 2 squared. And the third one is minus 1/4 over 3 factorial x minus 2 cubed. And then there's a dot, dot, dot after that. Okay. Now there are some, let's see, what am I sharing here? Some power series you should know. Go. Oh, we got some question maybe? Yes, that's true. Missed you a long time ago, Jacob, sorry. Just 2 hours have elapsed since your question, huh? You should learn some of the basic power series. This page says that the common ones a handful of the common ones, the ones that I would really like you to know are the one for the geometric series, a over 1 minus r is just the sum of powers on x. E to the x was, these numbers down here are factorials. They're easy to remember if you think of 2 as 2 factorial and 6 as 6 factorial. It's x to the n over n factorial for e to the x. Sine of x, cosine of x, where the sine is the odd powers, every other alternating series. These are all factorials of the exponents. So 540 is 7 factorial and 120 is 5 factorial. Cosine of x had the even powers. And the arctangent of x looks like this one, but shift the n over by 1. So if you shift these by 1, you get all these odd powers here. So they're easy to remember, and from those we could build almost any of them. Some other common ones would be a Taylor series for the natural log of x minus 1. So we move it away from the origin. We move it to the right 1 unit. Let's see if they have those in there. Here. Make that bigger. Yeah, this one is pretty handy here. The natural log of 1 plus x. These are all in your book. And let me hit that one here. Open big. That one we have. These are really the only ones I remember. I can fake the rest. But this one here is called the Binomial Theorem. And you've seen the Binomial Theorem before. Gives an expansion of 1 plus x to a power. But if you just know the geometric, e to the x, sine of x, cosine x, inverse tangent, this one's easy enough to take derivatives of to get. You wouldn't have to waste time memorizing that one. That one's easy enough to derive all the way through. If you knew those, that'll kind of save you some time on doing some of these power series. So one more thing I want to say about these power series. Let's go back and screen share with my green screen. When does a function have a power series? And if it has a power series, is it unique? Those are the existence and uniqueness theorems of the Taylor series. So let me write it down and then we'll talk about it in words. And then we'll leave. Under what conditions does a function have a power series representation? When a function has a power series representation, is it unique? So here are two big theorems that answers those questions. We won't prove them. If you have a function that's represented by a power series, then that power series has to be a Taylor series. In other words, the Taylor series representation for a function exists provided that all of the derivatives of the function exist. So if a function has a power series representation, then the variable x minus c, then the power series must be a Taylor series. So if you stumble across a power series representation for something, then it follows the formula of a power series. That is this kind of thing, say ak x minus c to the k, has the property that each ak looks like the kth derivative of f evaluated at c over k factorial. So all you really need are all the derivatives. So this answers the question on uniqueness. And then in order for this power series to exist, you've got to have a function that has all the derivatives. So the existence is spent upon, for the existence, what you need is f and all of its derivatives exist in an open interval containing that point C. So if f and all of its derivatives exist in an open interval containing C, then f of x is exactly equal to f of C plus f prime at C, x minus C, over 1 factorial. It has that Tander series expansion. If you truncate a power series after a certain amount, there's even a way to measure how close you are or how far off you would be. It's called the remainder theorem. I'm not going to make you learn the remainder. It's in your book. But look up in your book the Maclaurin series for some special functions, e to the x, sine of x, cosine of x, inverse tangent of x. Learn those, and then try to build other power series from those by term substitution, integration, or differentiation. And then some of the other ones are easy enough just to do from scratch. So next time, we'll talk about what I plan on putting on your test 1 week from today. Is that what I said it was? That's my calendar. 1 week from today is your next test. So I'm going to put a review sheet on Blackboard. And if you have time, go through that review sheet. We will also next time spend a bit of time talking about vectors and vector operations. That's what we do in chapter 9. But start reviewing for your test if you have the time. Any questions from anybody in here or at home?
I just want to talk to you about me.
Talk to you about you. Okay, well, we can wait till everybody's gone, or I can put you in a private room and we can talk when everybody's gone and we're not messing with your privacy.
We can just wait.
I'll wait. I got time. Anybody else have any questions? All right, adios. Sayonara.
See you Wednesday.
See you Wednesday. Maybe. When am I going to see you guys in class again? Never? We had a big full class today. Love it.
I was wondering if I could take the test early, or if I can take it online, because my parents can only come to pick me up this weekend,
Okay.
and the test is on Monday.
Which do you prefer?
Either,
We can do either one.
so I can take it online on Monday.
I'll probably have some folks taking it online. And all I need you to do is I'll send it to you in an email and you open it up and you have the opportunity to print it. Or put it on paper and send me just from Zoom in so I can watch you take it.
Okay.
Can do that?
Yeah.
Okay.
Okay.
Thank you. Okay. I'll take the cat and I'll come catch you. Sound good? Is that all right? Yeah. All right, Kat.
So, yeah.
Let me put you in a private room so that, or maybe I can stop the share. Wait a minute, I don't know how to do this. I got to put you somewhere so that nobody else hears you because it's going to be taped. So how about I stop? Do you need me to write stuff?
No. I just want to talk to you about like
Stop the
me coming back to
video.
class.
Okay, I'm gonna stop the video and let me see what I do to keep you from. Maybe I stop the recording. Where's the recording? Stupid Zoom thing here. Let me stop that recording. Okay. don't know how to stop that dang recording without stopping this. Okay. Stop the share. And where's this darn recording? Here, stop the recording. Boom.